Okay, is the sound working fine now? Yes. Okay, it's a great pleasure to be here. I have been working one way or the other with the black hole information paradox right from my second year of graduate school. I used to be a professor, knowledgeable group at that time, and we had a wonderful group of people who would sit down and argue about all kinds of things all the time. And this was when I got interested in this problem. And one way or the other, I've been just worrying about it for all these years. And I want to tell you where I think this problem has reached at this point. And I think we have a resolution which goes into string theory, but that's the story I would like to tell you today. So Hawking in 1974 came up with this puzzle. In general relativity, you have a prediction that you should get these amazing things called black holes. But then if you look at quantum mechanics, around the vicinity of black holes, you find that it is actually inconsistent. So that was Hawking's puzzle. And in a nutshell, what string theory is now showing us is that quantum gravity effects actually alter the structure of the black hole in a radical way. The reason that is surprising is that you might think quantum gravity works only at very short distances, characterized by the Planck length, which is 10 to the power minus 33 centimeters. So you should go back and ask what could possibly magnify the effect. So it could act across a distance of 3 kilometers. And the fact is that black holes always had one more hidden feature, which was pointed out by Bekenstein just a couple of years before the work of Hawking. As many of you might know, black holes have an amazingly large entropy, much more than the entropy of any matter that you would have the same amount of mass. So if you have this large amount of entropy, what does it mean? So nobody really knew what it meant, because normally entropy counts the number of states of a system, but we never knew what the states of a black hole were. But if you have a very large number of states in a system, then there can be certain effects from the measure in the path integral which you didn't anticipate. And so somehow what we are going to see is the effect of this large number of states actually magnifies the quantum gravity effect from being at the Planck length to being all the way out to 3 kilometers. So there were these two different puzzles. What is the meaning of this amazingly large entropy of a black hole? And then what do we do about the puzzle that Hawking raises about quantum mechanical inconsistency? And what we see now is that these two things take each other away. The moment we understand what large entropy means, then we can also understand how the information paradox is going to be resolved. And in a nutshell, this is the kind of resolution we get. In fact, as Ramesh mentioned in his talk, do black holes have hair? It turns out that in string theory, black holes seem to have a complete set of hairs. So all the states counted by Bekenstein and Bekenstein's entropy can actually be constructed explicitly for the very simple black holes of string theory. None of the states actually have a horizon, so they behave effectively for high energy processes as if they had a horizon. None of them actually have a singularity. We can roughly model effective processes as if they effectively had a singularity. But in fact, in detail, they neither have a horizon nor a singularity, and there are no information processes. So that's the kind of rough story I would like to tell you. Then I would like to spend the first half of the talk just telling you about the paradox so that we can see what the whole puzzle was all about. Okay, so here's the paradox. So gravity, as we know, is an attractive force. So if you have a mass capital M here, and a test mass little m here, and a distance of r, the Newtonian gravitational potential has a minus sign. And that's what's telling us that gravity is attractive. Of course, this mass has an intrinsic energy, mc squared, and so we place it near this mass capital M. What should we call the total energy of this mass? So just as a rough first pass at it in a Newtonian way, let's try to say we take mc squared and we subtract the gravitational potential. So you just add the energies in the rough way. This is very crude, but just to get started. But then you already start seeing something interesting. If this is the total energy of this mass little m, which is kept near capital M, then in fact, if you make little r small enough, the total energy actually vanishes. If you put it even smaller, the total energy is actually negative. So at r equals gm by c squared, you can see it becomes 0, and even smaller r, the net energy of this guy is actually negative. Of course, this is just a Newtonian approximation, and you should do this properly with gr, and when you do that, things don't change much. All you get is a factor of 2, and indeed it is true, if you keep something inside the horizon radius, the net energy of this guy can be made negative. So we see that if you add a particle but inside the horizon, this whole setup has less energy than what we started with by itself. But that's all fine. This is classical black hole physics, and even though it looks puzzling, it's not a problem. What Hawking noticed was that in quantum mechanics, even the vacuum is not completely quiet. it's always having these things called vacuum fluctuations. So from the vacuum, you can produce an electron-positron pair, let's say, and then the pair can annihilate and go back to the vacuum. So what we see as the vacuum in the room around us is actually bubbling with the creation and subsequent annihilation of all these particle pairs. Of course, because when you create the pair, it costs you energy delta E, twice the mass of the electron times c squared, it wouldn't live for very long because delta E delta T should be less than or equal to h bar. The fluctuations stay for a short time. But if you happen to have the same kind of fluctuation near the horizon of a black hole, you see that actually delta E can be made zero. The particle outside might have a positive energy. So we have already seen that a particle inside the horizon can have a negative energy. So you can arrange the total delta E to be actually zero, which then tells you that this particle pair can stay for an infinite time. In fact, now it's a real on-shell particle pair, and they don't have to reannihilate back. It's just simple quantum mechanical process. And this is the key to everything, because then you find the outer particle can drift out, the inner one just falls in, and the particles coming out, in fact, this radiation from the black hole, very low in the radiation, is called Hawking radiation. This is what Hawking found, that black holes want to radiate particles by this very simple process. The mass of the black hole has gone down because we saw if you put a particle inside this radius, the net contribution of the energy of that guy is negative. So black hole becomes slightly smaller. I tried down here. The process repeats. More particles come out. At the end, we don't quite know what happens. It may go down to Planck size, at which point we don't know the physics, or it may evaporate completely. But in any case, you have lots of particles coming out, and the black hole is evaporating away. If it stops at Planck size, we call it a remnant, a Planck size remnant. If it evaporates completely, of course, the guy is gone. Then what's the problem with this? This is a very interesting process, but the crucial process has to do with something called entanglement. Now, in quantum mechanics, you know that you can take, let's say, two spins and put them in an entangled state. So if you have one atom here which has spin up, another one here which has spin down, you can make a singlet out of them, up, down, minus, down, up. Now the whole thing is a singlet. But in fact, neither this atom nor this atom actually has a state by itself. The state of this guy is spin up if the spin of this guy is down, and the spin of this guy is down if the guy has a spin up. So the state of any one atom out of this pair of atoms is actually conditional on the other guy being there. You can define a state for the entire thing, but there's no state of one guy by itself. This, of course, is standard quantum mechanics, and there's nothing puzzling about it. The puzzle actually comes now, because now if you take a look at it, this electron-positron pair was also actually produced in an entangled state. When you have vacuum fluctuation, the electron could end up inside and the positron outside, or the other way around. In fact, you get a linear superposition of the two possibilities. So in fact, you get something which is, let's call the spin down. So down, up, plus up, down, and you have an entangled state. So whatever particle you are getting out as Hawking radiation, you can't be sure if you're going to get an electron or a positron. Whatever it is, it has a 50% chance of being either. The total state of the system is well defined. This is an electron if the other guy inside was a positron, and vice versa. The two guys are a triangle. Although this entanglement is actually very large, let's suppose capital N number of particles are emitted, then there are 2 to the n possible arrangements. That's called electron as spin 0 and a positron as spin 1. So in fact, all the guys inside could have been electrons, or all the guys could have positrons, and all these guys could have been electrons. Then I'll write something like this. But you have all the possibilities. You know, if you have a positron here, you have an electron here, and vice versa, you can see there are 2 to the n of these. So the amount of entanglement between here and here is very large. So now is where the problem comes. What happens when the black hole is actually gone? We said we don't quite know what happens near the end point of evaporation. Hawking initially assumed the black hole completely vanishes. It's getting, in fact, evaporating faster and faster. Smaller black holes have a higher and higher temperature. The whole thing might as well completely blow off and disappear. But now you can see the problem. What happens to all the radiation which is left? Energy has been nicely conserved. All the mass of the black hole is now in the radiation. So at least as far as energy is concerned, we are completely happy with energy conservation. But look at the state of these particles we have found. Is it this state, or this state, or this state? Well, it's none of them. It is actually a conditional state. It is this if what was inside was all ones. It is this if what was inside was a mirror image, 0, 1, 0, 0, or whatever is the mirror image of this. Now if this guy is a vacuum, and there's nothing left to entangle with, well, this guy can't have any state at all. So this was the violation of quantum mechanics that Hawking found. If I have two atoms which together are in a singular state, so I have spin up, down, minus, down, up, that's completely fine. But now if one atom out of this pair is completely disappears from the universe for some reason, there is no state left for the other guy at all. You can't say it is up or down, because it was up if the other guy was down and vice versa, and the other guy is now gone from the universe. So normally things don't go away from the universe, which is why we never faced this problem before. How come this time the guy managed to go away? And it all goes back to the fact that gravity has a negative side. You can start with a black hole of mass 1 solar, but when you put things sufficiently inside the black hole, as we saw, the net energy is negative. So the gravitational binding energy being so negative, you can actually add more particles, like we threw some electron or positron inside the hole, and yet the total energy can keep going down. It's the minus g m1 m2 over r that we are actually using. So you can actually end up with things which have zero mass, even though there was a lot of structure in there, and now if they have vanished, well, then you have a problem.
But after the entanglement continue to work, it's possible that it can get destroyed.
Well, that's fine.
In which case you can't say that there is no state left for the particles to come inside.
So it's very interesting. If you work this out in simple, we could just go to the quantum mechanics of the argument, and I could just come back and say, okay, what's the state of this? So let's go back to the two atoms. Suppose it is up, down, minus, down, up. And suppose you now say this guy is gone. So what is the state of this? You might say it is up plus down. Suppose a state has to be something. But here there's a problem, because when I wrote the state as up, down, minus, down, up, the word up plus down actually comes out in the x direction. Spin up plus spin down is sigma x. Why isn't it sigma y? Well, the reason it actually could have been sigma y, because you're saying up, down, minus, down, up, the singlet, I could have written I times up and I times down, because I could have minus I times down. I could have split it with various different phases. If I make the split with a different phase set, then when this guy is gone, I will left with sigma y. And that's why there's no state left for the guy on the right side. So in fact, you can't just say it's going to be the linear sum of these guys, because I could always add a phase to this side and the negative opposite phase to this guy. And so actually I don't know with what relative phases to add these guys, and that's why I can't do this. So it's a very pertinent question, but that's the
Even
problem.
if I take two particles which are entangling, they are taken far away.
That's okay.
Entanglement,
Taking them far away is not a problem. See, if in India, where you can take them as far away as you want. The point is, the overall system has a state. If you want to make a quantum state where one of the guys doesn't exist because the vacuum has no quantum numbers, then you don't know what state you have to do for that.
You could just measure it and gets the state.
Well, so as we saw in this case, if you want to add them, you can ask with what relative phases would you add.
No,
you
you
get
could measure
density
it.
matrix.
You will get density matrix. That is not exactly what Hawking statement said. You will get density matrix. So this was exactly Hawking's statement that in fact, this is what we I think should be saying here. The radiation cannot be assigned any quantum state. It can only be described by a density matrix. And this is what Hawking was complaining about, because starting with the system, when he made a star, you could start with a completely pure state, very complicated. It's just a piece of gas. It has some state. Normally when you have a state and you evolve it by Hamiltonian mechanics, you get a new state, e to the minus IHT on the initial state. So a state goes to a state. Doesn't matter how complicated the Hamiltonian is, but states go to states. Density matrices only come when you make approximations and you want to throw away some part of the data because you project out something for convenience. But here, whatever you do, because this guy is gone, and the guy is gone because the mass went away, and the mass went away because of negative gravitational potential energy, because this guy is gone, this time you have no choice. You start with a definite state, but in fact what you got left with was in fact a density matrix, and states evolve to density matrices. We actually don't know any mechanism which can do that. We don't have a setup of quantum mechanics where states and density matrices coexist at the same time, but in fact that's what Hawking proposed. He proposed that there are no S matrices for quantum field theory. He said there should only be something called a dollar matrix. Density matrices go to density matrices is the only real physics. Pure states are something special. But nobody has actually agreed with that very much because quantum mechanics goes beautifully everywhere else. And in fact, people later found there were troubles with that analysis. So nobody was able to make a theory where really the dollar matrix really takes over everything. So we'd like to hope that we don't have to do that. And let's see what the other possibility is. So in fact, people were so disturbed by that, they said, well, the eruption could stop when you come down to a Planck size remnant because at that time, quantum gravity would take over and we no longer know what should happen. But that's also a bit problematic because now, of course, the total entanglement is still maintained. But this guy must have these 2 to the n internal states. This state is correlated with this with this, and this with this. So this guy, which has Planck mass, has 2 to the n internal states. Well, how much is n? But n can be as big as you want. If you start with a black hole of 1 solar mass and came down, n would be something like 10 to the 77. If you started with a mass which is 100 times larger, n would be even larger. So in fact, by the time you come down to a Planck mass remnant, you can start with a black hole of any size, and n is unbounded. So in fact, within Planck mass and within Planck volume, you have to have an unbounded number of possible states. But in fact, that has never before happened in physics. If I limit both your volume and your energy, it seems that your phase space volume is bounded, and typically there's only one state per unit cell in phase space. So we've never been actually able to have a physical system which has an unlimited number of states in a finite volume and with a finite energy budget, one Planck mass. So even though this is not ruled out, and many people in general relativity who don't want to do string theory, they finally come and they accept this answer. There are ways to make things which hold an infinite number of states in a small mass. And for example, what you could do is, you could imagine that the baby universe starting here, where this is only the neck, and you hide all the data in the baby universe. It turns out baby universes are difficult to make because it requires some violation of positive energy theorems somewhere at the neck of the baby universe. There's negative curvature and somehow you can't manage without a violation. But it's a quantum domain, so you might say somehow you could do that. It's at least a possible solution. But in string theory, actually we find no randoms. In string theory, we can actually make all the states of Planck mass and there are no randoms. So this solution also wouldn't work. So let's summarize what we have seen for the paradox. We start with the pure state of a gas. It collapses to make a black hole. We can't seem to stop this in GR. Then the pair creation process happens, and we end, suppose you're left with a remnant and all this. Well, how can you have so many states on the remnant? And in fact, like quantum gravity theory, like string theory, we anyway don't seem to find any remnants. So how do we handle the problem? Well, of course, you could remove the problem if you never had a black hole in the first place. A normal star doesn't create this problem because you radiate from the surface and not from this vacuum pair production. So what if the black hole structure was different? So in GR, of course, you have pure space-time, and you have light cones that bend, and this, if you make a picture of some mass sitting here, the light cones bend and things go out in orbits. This schematic picture of GR. And then if you look at that in the context of black hole, what happens in the black hole, the light cones tilt in such a way at the horizon, this direction is time, and this is the radial circles at circular constant radius. As you go inside the horizon, light cones tilt in such a way that everything has to fall in, nothing can come out. So once you have this kind of a horizon, once you have something which comes close to making a horizon, it's very difficult to not let it make the horizon. You can't put a surface here and expect it to stay, it just gets sucked in. Because the light cones point in, that's why the whole no-head theorem comes. And so roughly this is what the no-head theorem is. If you try to keep a rocket very close to the surface and say, hey, just stay there, you need to have an enormous amount of exhaust gas pressure to keep the rocket there. If you keep it closer and closer to the horizon, the amount of pressure required is infinite. And so sooner or later everything falls in. And even if you had strings, it would just fall in, and the black hole goes back to its old ball form where you have no hair. And that's the statement of Wheeler, black holes have no hair. So in fact, just to summarize this part of the talk, the information paradox is a combination of two observations. The no-head theorems tell you that the black hole has to have a vacuum at the horizon because everything gets sucked in. And once the vacuum is sucked in, you get this pair creation process, which is ordinary quantum mechanics, and people have studied over it for ages and they have seen there's no way to get out of it. And once you get this pair, you have the entanglement problem. And as the black hole disappears, what do you do at the end? You can't be entangled with nothing, and you can't be entangled with a tiny, tiny remnant. Both look very hard to do. So what's the correct physics? So we're going to go and see that in string theory, something else happens. The no-head theorem, in fact, gets paradoxed. And so in fact, the black hole becomes much more like a normal object. It does have a normal surface. If we have a star, all the data of the star is on the surface. It's not like there's a vacuum from which radiation comes out. Radiation actually comes out from what is happening on the surface, and the black hole now has a surface. The no-head theorem will be bypassed. This surface will not get sucked in, and we have to see why not. So this is the structure. First balls are listed here. Lots of people who have worked on it and contributed to the subject. I was summarizing in a very schematic way the kind of ideas that have been learned here. So first, consider a very rough analogy to first balls. This is a slightly complicated structure to explain what the first balls do. But if you look at a simpler example, it might be easier to understand. In 1982, Ed Whitney came across something called a bubble of nothing. And I'm wondering if some people here might be familiar with this. It was the following idea. Let this be Minkowski space-time. It's 3 plus 1 dimensional, but I just draw one dimension, let's say x over here. But suppose he also had a compact dimension, a fifth direction. So there was a small compact circle, so now the whole space-time looks like a straw. I'm not drawing the other one, it's a compact circle. But there's no mass or anything, so it looks like it's a completely simple and stable situation. But actually it's not stable. What Whitney showed is that this space-time is unstable to tunneling in the following sense. So imagine this to be like a drinking straw. You can pinch the straw in the middle, and then break it apart, and then you have no space-time here, you have a gap. And then you close the straw over here smoothly, like the end of a cigar, and you close this straw over here smoothly, like the end of a cigar, and there's nothing here. So this is a completely compact and well-defined space-time. You come on, if there was an ant crawling on the straw, it would come here, and then go down here and come back. So it's not like you fall in the middle of nowhere, But this space-time is unstable to going into this. This was a 1D picture, but it was actually talking in 3+1 dimensions. So in more dimensions, you get the same situation. So if this bubble was to nucleate in the middle of this room, you would cut out a whole sphere in the middle of this room. Let's say there, in the middle of the room, a few meters in size. And then the compact circle, which is living at every point in space-time, there was an extra dimension. As it comes near the surface of this bubble, it just pinches off and closes like a cigar. From every angular position, it comes and closes. So there in fact is no space-time here. That picture doesn't exist in space-time. The whole thing is a different topology, and in this topology you have this solution. And not only that, 3+1 Minkowski space with one extra circle is unstable to terminate into this solution. Okay, so people don't worry too much about this instability. Of course, we need compact dimensions for so many things. Yes, please.
Did you draw space or did you draw space-time?
I only drew space. People didn't worry about it too much. It's been known for a long time because it turns out if you have spin half particles, you don't have consistent boundary conditions on this cigar. You know, if you have spin half, then somehow you need minus signs, and it turns out the tip of the cigar you need a singularity. But when you come and do this with string theory and the small changes between this and what you actually get in string theory, that will actually get handled. So it actually works out beautifully by itself. But now let's see if this kind of picture has something to suggest about what we have learned in black holes. So in 3 space and 1 time dimension, this was our picture. If you put a particle in here, it had negative energy. Now out of all these dimensions, suppose just draw one dimension to make contact with what we were just talking about. Here's the mass at the origin, this is the horizon radius from here to here, and as we said, if you're in there, you have net negative energy. Because the gravitational attraction becomes so much, it overruns the mc squared, you have net negative energy. Now what if we had an extra compact dimension? Well, then I would draw this like a drinking straw like I was doing, and of course people have known about extra dimensions for a very long time. They seem to have no particular significance for black holes because across this radius, which is like 3 kilometers, a Planck-sized circle would just go smoothly across. The Planck size just outside that, the Planck size just inside that. You would think it's a completely factored geometry. Something may happen at the origin, but you would think nothing happens at 2gm by c squared. So you can still go in here and have your net negative energy. And so that was a standard model. Even if you knew about compact dimensions, nobody worried about the fact to do anything special at the horizon of a large black hole. But now it turns out there's a completely different structure possible with the compact dimension. As you come near the place where the horizon would have been, suppose the whole thing pinches off like a cigar like this and this. In fact, there's a twist in the pinch off. It could be called a positive or a negative twist, and makes a gravitational structure called a Caruso-Klein monopole. It's just a gravitational structure which you may or may not have heard of. The details don't matter right now, but it is important with the extra space-time, we can actually have both Bose-Einstein and Fermi wave functions, which we didn't need to have. So in fact, it turns out that all the mass of the black hole which we had in that big central red dot M is now captured by the curvature of the surface. And now there is no place where you can actually go in and have a place with negative energy. So now what has happened is that we have completely changed the topology, and the reason that this thing doesn't actually fall in is because it sort of ends like a cigar. In fact, if you look at the bubble of nothing that Britain had, the bubble pinches and then expands outwards at the speed of light. It actually wants to blow out. These guys don't grow, so pinch out and go, they go up to the horizon, and then a few Planck lengths out to the horizon, they stabilize, and those are the fuzzball structures that we found. So what did we actually compute? So in more dimensional thing, this was again a one-dimensional picture. In more dimensions, the inside of the horizon is completely emptied out. Like we just said, happened in the bubble of nothing. There's nothing in the inside. As you approach from any of the other directions, the compact direction, in string theory you have 6 compact dimensions, total dimensions 10. So you have 6 compact dimensions. Those compact circles will come all over here and get pinched off. And they can get pinched off with a plus twist or a minus twist in different angular directions. So if you have a Planck-sized compact circle, there's roughly one choice of plus or minus on one bit of data per Planck length squared of the horizon. And if you play with the idea of Beckstein entropy for black holes, you know that's just about the entropy you want. Every Planck length squared of the horizon should have roughly one plus or minus one bit of data, and that's the order of the entropy of the black hole. So what have we actually done? So if you look at the structure, we're just drawing these things as the points here, some are plus, some are minus. This structure is called a fuzzball, and inside that there's no space-time. Space-time comes and ends with this new topology. Yes, please.
Sorry. Why is it so in the case of the Caruso-Klein instability, you have a particular tunneling probability, but now you're saying that any black hole space-time with high dimensions,
Will have this
compact, is there any reason to say that, I mean, the other one comes, is there because of a dynamical process, right? Because of
I will,
instability.
I'll talk about it in a second.
Okay.
Yeah. So the question here was that you can actually compute the amplitude for that kind of tunnel, and in the bubble of nothing situation, there's an amplitude which you can compute, and on grounds of units, with the compact dimensions Planck length, the amplitude is order 1 per Planck time per Planck length cube. So it's a not small effect. So this Planck scale go almost instantly. Here also you can see there's a path by which you tunnel from ordinary spacetime to the Fuzzball spacetime. You can find topological path. I'll show you an estimate of the tunneling rate. Tunneling rate is small because you are tunneling a macroscopic object to a macroscopic object. It's very small. But the point is, as I said at the beginning of the talk, you have to multiply it by the factor of how many possible things you can tunnel to. And that is the biggest entropy for a black hole, and as you know, that's a very, very big number. So that's the cancellation we're going to see in a minute, that even though the amplitude is very small for going into any one solution, the new thing we have seen this time, which we didn't have in the bubble of nothing, is now we have this plus or minus at every step, and now all the states of the black hole are given by these different choices. So you have a huge Beckstein entropy number, into the Beckstein entropy number of possible directions to go to, and the amplitude of tunneling to any one of them is small, but you multiply the Beckstein entropy, and the amplitude becomes all. That's the magic.
Space-time is just outside the horizon or inside?
Space-time is just outside. As we saw, you can see from this picture, space-time ends here because the compact circle got pinched off, so nothing left inside. So what the actual calculation we do in string theory to get this picture? In string theory, basically you can take a gravitational coupling and make it from weak to strong. So it's a parameter, so you can do what you like with it. At weak coupling, you just have some strings and brains, you know everything how to play about with them. And people thought in the early days of string theory, as you go strong gravity coupling, when gravity is switched on, you should get a normal black hole. All the matter sitting at the center, and you get a horizon, and you should get wave production, that's what you should get. But with the engineering technology in string theory, what we were able to do is to take all the possible states of a string with a given mass, and then increase the coupling, and each case you can actually find that it doesn't go here, it actually goes to the Fuzzball. The thing actually compared to the coming pinch, and for the simplest black hole, what we call a two-charge black holes in string theory, you can actually take all the states. You can count them, you can quantize them, and you can exactly look at them. You know there are no other states. So for the very simple black holes, all the states can be constructed, and they all give their, so you know there are no other states, and they're all of the Fuzzball kind, not a single guy which has a horizon. So what I mean by saying the simple black holes, in string theory normally work with black holes which are close to having maximum charge. They are like Reichenbach black holes with maximum charge, and we start working with charge into less than the mass. It's just more stable to start that way. So we can't get close to Schwarzschild black holes immediately. So that's the step in which we can always say maybe it was literally for Schwarzschild black holes, but we see no reason for that. For extremal black holes and near extremal, we all get the same picture. Okay, so as I was just answering in response to the question just asked, how did the classical intuition get broken down so badly? And as we said, this is how the states seem to behave, and then of course there's no information paradox. You have a normal surface, and we can compute a relation from that surface. We check the relation from simple Fuzzball solutions, and they give exactly the kind of rate that Hawking relation would like, down to the last factor of 2 and pi. But the information problem is not there because not behaving like a piece of coal with the same temperature. It has a normal surface. It's not coming out of vacuum per production. So we just ask the question that I was just trying to answer in words. When a star collapses, it seems to, you can just follow the gravitational collapse, looks completely good to classical approximation, everything goes to the center and makes a horizon. What can possibly violate this classical intuition? And as we said, we have all these bubbles of nothing, when you have this new topology, but how do you access that topology? There's another solution, but is that where you're really going? So of course you can actually first check that there's an amplitude, just like in Newton's bubble of nothing case, to tunnel from this down to this. For that, just have to look at a path in superspace or the space of all possible solutions. Between two topologies, you can have a path. And then because always some point tunnel from anywhere to anywhere, you could run into a wall and have some small amplitude for tunneling across the wall and not just smashing out. But normally we of course ignore this kind of tunneling for macroscopic objects. It's just something special about a black hole. And as I was just saying, in 1972, Beckstein taught us that black holes have an enormous entropy, basically given by the area of the horizon in units of Planck length squared. A solar mass black hole then has an enormous number of states, which is 10 to the power 10 to the 144. This is far larger than the number of states of normal matter with the same energy. And the question is, does this mean anything? But till now we didn't actually know what this entropy was counting, but now we know what it is counting because we can actually make all these wave functions for simple black holes in string theory. So now we have an amplitude to go from here to here, tunnel from this to this, this to this, this to this. And if you have many different things you can tunnel to, you have to multiply by the number of possible final states, like you do in any particle physics calculation. So my amplitude for tunneling to any one of them will be exponentially suppressed. I'll just give you the number in a minute. And I have to multiply by the Beckstein entropy, which is actually exponential of the mass squared. The number of states is exponential of the mass squared, and we'll see the two coefficients actually exactly cancel. So let's see how this calculation would go. First, let's look at a toy model. If you take a shell of mass falling into make a black hole, it will start emitting some particles even as in its initial collapse, but they'll be very few in number. But suppose